Hello. Today we are going to be talking about Chapter 2, Chemistry of Life, which is page 17 in your textbook. Did you know that the human body is 96% just 4 elements? Carbon, hydrogen, nitrogen, and oxygen. Most of that is in the form of H2O, which is water. As you know, we're about 70% water, so most of that hydrogen and oxygen is locked up in that. To understand chemistry is to understand the foundation upon which all the other systems in this book are built. If you understand how chemicals interact with each other, then it's a little bit easier to understand when we talk about the urinary system and sodium being reabsorbed because of the things that it does for the body. Or when we talk about potassium and carbon and hydrogen and how those things interact with each other inside the body. So chapter 2 is really a foundation chapter. And like I explained, we are not going to be balancing chemical equations or anything like that. This is mostly just an introduction to how elements work. So let's get started. Share my screen, sharing my screen. Okay, here we go. So we have the chemistry of life. So this isn't biochem, this is just chemistry in general. Okay, so before we start, we need to get a couple of vocab words out of the way. When you were in high school and you took chemistry, you probably learned these. Matter is anything that has mass and takes up space. Mass is not necessarily the same thing as weight because weight is relative. Weight is based on gravity, actually. The more gravity, the greater the weight. The less gravity, the less the weight. But the mass of something doesn't change, but the weight can. So mass is not the same thing as weight. So matter is anything that has mass and occupies space. So you are matter. An element is a pure substance, and what that means is it just can't be broken down into anything smaller. A compound is a chemical combination of 2 or more substances. And of course, I'm wearing my chemical compound shirt here. This is actually supposed to be representative of DNA. I thought it was appropriate for today. Okay. Before we go on to the next slide, you'll notice that the PowerPoints don't cover every single thing in the book, so every once in a while I'm going to pause and talk about something else. So we are on page 18, Basic Structures of Life. It talks about the different proportions of elements that are found within the body. So we have major elements, as I mentioned, oxygen, carbon, hydrogen, and nitrogen. They make up most of you. We also have calcium and phosphorus. And where do you think the calcium and phosphorus are found? Yeah, in the bone. Exactly. So those 6 elements account for about 99% of your whole body. You have some lesser elements and then some trace elements. Some of the lesser elements, sulfur, potassium, sodium, chlorine, believe it or not, magnesium, and iron. Do you know where iron is found? Yeah, iron is actually found in your blood. It's locked in your blood cells. It's part of the hemoglobin molecule. So you have a little bit of iron. Let's see, some trace elements. We have chromium, cobalt, copper, fluorine, iodine, and manganese, which is always fun to say. Anyone know where you find iodine in your body? This one's a little harder. In your thyroid gland. Yes, your thyroid gland actually uses iodine to make its thyroid hormones. So you do have to have iodine. Now, where do we get most of these elements? That's right, we get them through our food. So anything that we take in, we can process out some of the elements that we need, and our body will use them in various ways. And of course, as we go through this course, we will talk about some of these different elements and how they work in the body. Okay, now, we actually missing a slide here, but that's okay. All right, before we go on to protons, electrons, and neutrons, I actually want to talk a little bit about the structure of an atom, because I think this is a little backwards. So if you take a look on page 19, it shows you an atom, and you have a center or nucleus, and then you have things that are whizzing around on the outside of the nucleus, and those are electrons. Now, within the nucleus, you have protons and neutrons. Protons carry a positive charge. It's alliterative. Protons, positive. That's easy to remember. Protons carry a positive charge. Neutrons are so named because they are electrically neutral. They do not have a charge at all, but they do contribute to the overall mass of the atom. So we count them in a way. So protons are positively charged, neutrons, no charge at all, and then electrons, which are much smaller than protons or neutrons, have a slight negative charge. Now, electrons are so small that we do not count them in the atomic weight or atomic mass, because first of all, we don't even know really where they are, because they whiz around the nucleus so fast that we can't ever see them. We can only ever see where they've been, not where they are. So they're so small and have such little mass that they don't count towards the total. So we have protons, neutrons, and electrons making up an atom, but only the protons and the neutrons are added in the total weight. So if we go back up here, protons carry a positive charge, electrons carry a negative charge, and neutrons don't. They're electrically neutral. They're like the Switzerland of atoms. Okay, so there is an animation on the Davis Plus website about the atom here. We're going to move on in the slides, but then I'm going to come back. All right, so since we're talking about weight, each element carries a unique number of protons. So the atomic number is the number of protons in the nucleus. The atomic weight is the number of protons and the number of neutrons, which I just mentioned. So the neutrons and the protons weigh enough, again, I use the term weight, but what I really mean is have enough mass to determine the weight of the atom, which of course is exponentially minute. The atomic number is the number of protons, and it's the atomic number that we typically think of when we're looking at a periodic table of elements. So I'm going to see if I can bring that up here. I have to move some stuff out of the way here. There we go. Okay, so this is a typical periodic table, and first of all, Dmitry Mendeleev invented this. You may have heard his name before. His was a little bit different than this, and since he invented his, there's been 700 different variations on this. So they are all slightly different, but this is one that is most agreed upon. So what we have here is iron, Fe, and then up in this corner, you have the atomic number. Now, what does the atomic number represent again? Yes, the number of protons in the nucleus. The number of protons is the atomic number. Good. So 26 is iron's atomic number. And then on the other side here, in the other corner, you have the atomic mass. It's always a little variant between chart to chart to chart, but you get an idea of how much the protons and the neutrons weigh inside the nucleus of an iron atom. And it's 55.845. That's the atomic mass. Now, the periodic table lists elements that have similar characteristics together, and I like the way that it's colored. It makes it easy to pick certain things out. For example, over here, these blues, these are the noble gases. So you have helium, neon, argon, krypton, xenon, and radon. And they all share similar properties to one another, which is why they're lined up the way that they do. So if you ever take a look at a table of elements, you don't really need to study one for massage therapy. You get the idea that even in rows, they are lined up by their atomic number, but in the columns here, they share chemical characteristics. So it's pretty brilliant, actually. All right, back to our slides. All right, so the atomic number determines where its place is on the periodic table of elements. And the atomic weight is the protons plus the neutrons. So if we go back up here, we have, let's see, 2, 4, 6 protons. 6 protons, or am I missing some? Oh, no, I'm sorry. I was just looking at the book and it was talking about oxygen and I got confused for a second. No, this is 6. So who knows what this is if it's 6? It's atomic number 6. Well, if you don't know, let's go back. Where's number 6? That's carbon. Yeah, carbon is 6. So this is an atom of carbon. Sorry for the confusion. I shouldn't try to look at the book and speak at the same time. Okay, so this is a carbon atom. So you have 6 protons. That's what determines whether or not it's carbon. Or oxygen, which has 8 protons, or hydrogen, which has 1 proton. Now, the electrons don't really determine anything yet as far as what kind of element it is. The electrons are going to come into play when we're bonding elements together. Now, electrons, like I said, are whizzing around the nucleus, and they go in different directions all the time, and you can't ever see them because they're moving so fast. And again, we never can see where they are. We can only see where they've been with an electron microscope. So we have an idea of how many electrons are surrounding a nucleus. They are, as we have learned, sort of divided into energy shells. So the first shell or energy level is called a valence. So it's a valence shell. And the only reason I bring that up is because we have a type of bond called covalent, and that's going to make more sense now that we know that this is a valence shell. The first energy level or first valence shell can only ever hold 2 electrons, just 2. So no matter what element it is, the first valence shell is only ever going to hold 2 electrons. After that, every other shell after that can hold more. Most textbooks say that the second energy level can hold 8, the third, fourth, fifth, they can vary. So we only really ever talk about the second energy level here in this book. So that we're going to go with 8. So the second energy level or second valence shell here can hold 8 electrons. Now you see that in carbon, you only have 1, 2, 3, 4. So it could hold how many more? 4, right? 4 more electrons. And that's one of the reasons that carbon can bond to another carbon, because you have 4 on one carbon atom and 4 on another carbon atom. They can have a complete second valence shell if they get together. Okay, so 2 reviews. Which of the following is pure substance and cannot be broken down into 2 or more substances? What do you think? If you said B, you are correct. Good job. Pat yourself on the back. Okay. Now, We are going to move on to chemical bonds, but I'm going to do a separate video for that. So before we do, I want to talk a little bit about isotopes. You do not have a slide for isotopes. So I'm going to stop sharing. So if you take a look in your book on page 20, an isotope is an element that has a different number of neutrons, essentially. Let me share this since we don't have a slide. See? Okay. Your book talks about isotopes of hydrogen. So hydrogen only ever has one proton and one electron whizzing around the outside. It is the simplest element, and it is also the most abundant element in the universe. Almost everything is made of hydrogen. Now, an isotope of hydrogen is when a proton comes together with a neutron and you still only have one electron. That's still hydrogen because it still only has one proton. Remember, the atomic number, in other words, the number of protons determines what element it is. So this is still hydrogen, however, it's heavy hydrogen, okay? Because it has a neutron attached in the center. So in your book, deuterium is an isotope of hydrogen. It still has the same atomic number, but it has a different atomic mass. And if you take a look at periodic table of elements, it doesn't list isotopes. Some of them do, but not all of them. Now, you do have a second isotope of hydrogen. It's called tritium, and it has one proton and two neutrons. If you take a look in your book, you can see that. Tritium is radioactive. Its nucleus is really heavy, and because it's so heavy, it starts to break down. And it breaks down over time, and as it does so, it releases radiation, and that's what makes it radioactive. They are inherently unstable because they're too heavy. That's really the gist of that. Excuse me. Isotopes that are radioactive are called radioisotopes. We do actually use radioisotopes, not in massage therapy, of course, but in medicine in general. We use it for chemotherapy, for radiation treatments. That's actually what we're using is radioisotopes. Some of them are more radioactive or more unstable than others, like plutonium. I mean, we're not going to use plutonium in medicine, but we can use isotopes of hydrogen and other elements. Okay, you do have a life lesson on page 20. It talks about radiation therapy. You can read that on your own. And of course, if you have any questions about anything that I have said in these videos or anything that's in your book, the Chemistry of Life discussion board is the place to post those. I'm asking that you not email me directly, that you post your questions on the discussion board, because it will be the most efficient way for me to answer those questions and kind of keep everybody on track. Also, I encourage you to read other people's questions too, because they may have the same question that you do. So please post on the discussion boards. It is a requirement. It helps me figure out whether we're all on the same page or if there's any way that I need to tailor the information a little bit differently. Or if there's something that you say, Carrie, I really did not understand what you were talking about, that's totally fine, okay? So when we come back, we're going to be talking about chemical bonds.